Hello everyone and welcome back to this lecture on aquatic geochemistry. This is the 19th lecture and we are going to continue understanding the thermodynamics and thermokinetics concepts. So, in our previous lecture we were discussing about the Gibbs free energy and the chemical potential of a particular species, how to calculate that. Now, let us move on to finding out what is the chemical equilibrium, how to calculate the chemical equilibrium constant, that is K. Now, chemical reactions are characterized by this equilibrium constant K. Okay. Now, this constant, what is this constant term represents? It represents the products divided by the reactants. It is the ratio, okay, it is the ratio of the product terms divided by the reactant terms. Okay. You may have 4-5 products here, you may have any number of reactants here, you just go on multiplying them in their concentration terms. Okay. What is very important here? When you are writing a equation, okay, you have to always balance the equation and see that all the charge balances and every molar mole to mole calculations, they are correct. Okay. So, the molar corrections has to be checked and the charge balance also has to be checked. Okay. So, that you have to be very careful about. Now, let us first begin with an example. Okay. Why do we need to find out the equilibrium constant in aquatic geochemistry? Okay. An example, a very common with a very common mineral. One of the first minerals to form during evaporation of seawater is gypsum. Okay. Rocks made up of gypsum are therefore very often found in the geological record. That means, in the stratigraphy, wherever there is a sedimentary upliftment from the oceanic conditions, there you will find lot of gypsum salts rocks. Okay. Therefore, gypsum, which contains this element sulfur, okay, as sulphate SO4, these can be used to obtain a record of how the stable. Okay, so if you are going to do a isotopic evaluation and you want to see how it has evolved over time, how sulfur has evolved over time, then we do this isotope composition called the delta 35S. We are going to measure that. Okay, we are going to measure the isotopic composition of sulfur in the gypsum rocks. Okay, so, delta 35S, and how this isotope composition varies with time will give us an understanding of how this particular element has evolved with time. Okay. How it was in the past, how it will help us understand different events that has happened to that particular aquatic system, either it is a ocean or ocean is not an unreactive body, it is continuously reacting with life, it is continuously reacting with the climate. Okay. So, any climatic related changes, any biological major events that will change the delta 35S value, the isotope composition will change. Okay. Although we have not gone into isotopes, this is a very general discussion that we are doing, that just to show you how connected things are. It is not that when we talk about isotopes we have to absolutely forget about our thermodynamics, we still use somewhere. And specifically in geochemical modeling, if you are trying to model a system, okay, and you are trying to model the past and with temperature and how temperature has evolved, thermodynamics is extremely important. Okay, the application of thermodynamics. So, this equation, therefore, we write that is gypsum, that is CaSO4 dot 2H2O, it is a hydrated form. This will form Ca calcium 2 plus SO4 2 minus plus 2H2O. Okay. And the equilibrium constant value, okay, equilibrium constant value is equal to 10 to the power minus 4.58. Okay, that is calculated. That is calculated in experimentally in the lab. Okay. pK, okay, pK value is equal to, now pK, what is pK? That is the minus log K. Okay. Minus log K value if you take, that is equal to just this one, the power value. So, 4.58. Okay. Now, how do we calculate that? You know, this is just easy understanding of notations. Okay. So, pK value is minus log K value. Okay. So, if you have a value of minus 10 to the power 458, so this becomes only 458. Okay. And if you have a very complicated number, okay, you can easily try to rearrange and make it in simple numbers, but of course that may not matter much if you are having a scientific calculator. Okay. So, this is just understanding the notation. Now, whether a reaction is happening or not. Okay. First thing, if how do we write the equilibrium constant term, that is K. K is equal to activity of calcium 2 plus calcium 2 plus into activity of SO4 2 minus into activity of H2O whole to the power square divided by CaSO4 dot 2H2O, that is a gypsum. So, this is a coming from this equation. Okay. So, this solubility if gypsum is dissolving. So, this is our reactant and this is our product. Okay. So, this is our reactant and this is our products. So, when we are going to write the K term, we are having all the product terms divided by the reactant term. Okay. Now, since this is a what kind of equation? It is a solubility equation, right, it is a solubility, gypsum is dissolving in water. Therefore, these type of equations are also called the solubility product. K is then called Ks, okay. K is then term called the Ks and that is called the solubility product. And since it is a solution, we are not going to write in terms of concentration, we are going to write in terms of activities. Okay. So, as compared to C terms, we are going to write A terms. Okay. Now, activity, as I have already explained, it is the effective concentration. Okay. So, it is the effective concentration that is doing the reaction, that is actively doing the reaction. Okay. And it is always raised to the power of the stoichiometric coefficient. So, that is why balancing the equation is extremely important, because if you are not balancing the equation, you will not raise this, you will not know the power and you will not know, so you will not know the coefficient, stoichiometric coefficient, and therefore, you will forget to raise it to the power and therefore, your value will be wrong. Okay. So, always therefore, balancing of equation is very important. If it did not have been a very dilute solution, what would happen? The absolute concentration C, okay, that is written in terms of this third second bracket, box brackets, okay, this will be essentially equal to the activity. Okay. So, in the ideal case, okay, in an ideal solution, okay, if the ions are very dilute, okay, then the absolute concentration is equal to the activity. So, you can write A calcium 2 plus is equal to concentration of calcium 2 plus. Okay. So, these are few things that we are we are just discussing. Also the thermodynamic convention is to set the activity of solvent and pure solids equal to 1. This is what we have discussed in our last lecture, that in case of pure water and pure solids, their activity is equal to 1. So, here we are having this gypsum whose activity will become 1 and H2O will also become 1. So, here this term becomes 1 and this term also becomes 1, okay, because this is a pure solid, okay, this is a pure phase, pure solid phase, and it is a pure solvent phase. Okay. So, my Ks therefore becomes activity of calcium 2 plus into activity of SO4 2 minus, and since it is an ideal solution, in ideal solution it can be written in terms of concentration. Okay. Therefore, we have them in terms of concentration terms. Now, let us do some very easy calculations. Okay. Imagine we are going to take 3 hypothetical cases and we are going to see how the reaction is happening, because those kind of questions we are going to answer in thermodynamics, understanding of thermodynamics and their application in aquatic geochemistry. So, first case, if the calcium concentration, which is also equal to the sulphate concentration, is equal to 10 to the power minus 3 moles. Okay. The product therefore becomes, okay, you are going to multiply then and it becomes 10 to the power minus 6. Now, this is less than the value of Ks, because we have already seen that K's value is equal to 10 to the power minus 4.58. Okay. Now, here my K's value is 10 to the power minus 6. Therefore, my solution is undersaturated. Okay. Their concentration is very less. That means, there are too few products relative to the reactants. Therefore, the reaction will shift to the right, which means any solid present will dissolve. Okay. So, in this equation, this is less than the K's value. Okay. So, here the reaction will proceed towards this direction and the reaction will, the solid whatever is there, it will go on dissolving. In a case where both the concentration terms is equal to 10 to the power minus 2.29 moles, then the product of these two terms becomes 10 to the power minus 4.58, which is exactly equal to the value of the Ks, okay, solubility product. Then we are going to say that now the solution is at a saturation equilibrium. And what do we mean by equilibrium? That how much the solid phase will precipitate and in equal amount will also dissolve. So, precipitation and dissolution will happen at the same rate. Okay. This, as long as this is maintained, okay, that means we are talking about an equilibrium. Forward reaction is same as backward reaction. As much as it is dissolving, same amount is also going precipitated. Okay. Another case. Now, if the calcium and the sulphate concentration is 10 to the power minus 2 moles. So, now the product becomes 10 to the power minus 4, which is greater than the value of Ks, that is 10 to the power minus 4.58. Now, the solution is super saturated. That means, there are so many products as compared to the reactants. Now, only the reaction will shift towards the left and only precipitation will happen. You should always remember that we are considering the product and not the concentration of any single species. Okay. So, how we are going to understand whether a reaction is moving in a forward direction, whether a reaction is at chemical equilibrium, whether a reaction is going in the backward direction. Okay. We are going to find out the K value from the K value. Okay. From the concentration, try to find the K value and see what is the equilibrium constant. Okay. Now, next is our Gibbs free energy. Okay. From the K value, we are now going to find out the Gibbs free energy value. Okay. That is the G. And there are 3 types of G that we have already discussed. First is the standard free energy of formation. Okay. The free energy of formation of every compound. Okay. And it is at a standard state. So, therefore, the delta G naught F. Okay. This naught means that it is at a standard state. Okay. The energy content of 1 mole of a substance at a standard temperature and pressure, and this is almost always at 1 atmospheric pressure and 25 degrees Celsius. It is the energy to form 1 mole of a substance from stable elements. Now, we are forming compounds from the elements under the standard state conditions. That is the energy required to form 1 mole of that particular compound. Okay. For example, okay, and definitely for all elements, delta G of 0 is equal to 0 at STP. Okay. In the stable form at STP, delta GF for elements is equal to 0. That means, if you are taking calcium in its elemental form, okay, that elemental calcium powder, okay, that delta GF 0, the GF 0 value is equal to 0. If you are forming calcium oxide, therefore, you need oxygen as the other element. Oxygen is stable as oxygen gas at STP. Okay. That is the most stable form of oxygen. For O2 gas, the GF 0 value is equal to 0. Okay. Now, what is the free energy formation of calcium oxide? So, here if we are going to write, first we are going to write the equation, okay, that is calcium plus oxygen is equal to 2 CaO. Okay. So, if this is the equation, okay, what is the delta G of, this is F, okay, what is the delta GF value of calcium oxide? Again, as I said, elements, their value is equal to 0. So, 0 plus 0, and this is measured. Okay. Whenever a reaction is happening, you can measure the energy changes. Okay. You can measure the amount of heat that is released, the heat that is uptaken. Okay. So, that we are going to measure. Okay. So, that value you have. Okay. And for every element, and not element, element is 0, for every compound it is calculated. Okay. What is the delta G0F value? Okay. So, this G0F value for every compound is measured in the lab, and we have in any, if you pick up any physics book or any chemistry book, you will have this in the tables, in the appendices there will be this values given. Okay. Now, what is the free energy formation of calcium oxide then? It is just this value. Okay. It is that value. Okay. So, for this reaction, okay, for this reaction, the delta G0 R value is 2 into minus 604, which is this value. So, for the formation value becomes the delta G0F calcium oxide. Therefore, if you divide it by 2, because here you are forming 2 calcium oxide, it comes down to minus 604.2. Okay. So, this is our value. Now, this is the most, that was, this particular example is the most easiest example that one can pick up. Okay. From similar methods you have to apply for calculating any compound. So, if you are trying to calculate a compound from its element, it will just be, you just find out what is the G0F value from the given tables. You will be given tables, you will just find out what is the del 0F value. Okay. Now, we are moving towards a reaction now. Okay. So, for a reaction, the energy that is released or absorbed by a chemical reaction, okay, with all substances in the standard state, okay, because this is a standard state reaction, that is the standard free energy of reaction. So, all the reactants are in the standard state. Okay. Then the del G0 R is equal to summation of delta G0 F of products minus summation of delta G0 F of reactants. Okay. So, it is just products minus reactants. For a very generalized reaction, let us see in terms of reaction. It is, suppose this is a reaction, that is B plus C is equal to D plus E, okay, and you have these coefficients, okay, small b, small c, small d and small e. How are we going to write it? We are going to just multiply the coefficient. So, here this is my, what is this? This is my product and these are my reactants. Right. So, it is my product minus my reactants. So, delta GF is that the formation energy of D, and it has to be multiplied with the stoichiometric coefficient. You just go on sum. So, this is summation, right. So, sum plus whatever E into again delta G0 F E minus all the same reactants, sum of the delta GF of the reactant compounds. Okay. So, this you can calculate, right. These values for every compound is given, for every compound it is given. Okay. For pure solids, solvent, ideal gas, ions at 1 molar, it is always equal to 1. Okay. We note that. Okay. Now, after you find out all these values, you just multiply it with the stoichiometric coefficient. After you multiply with the stoichiometric coefficient, you do this product minus reactant subtraction, and that is your delta G0 R, very simple. Using this delta G0 R, we are going to find out what is the equilibrium constant. Okay. So, the equilibrium constant K value is calculated from the delta G0 R. Using this equation, delta G0 R is equal to minus RT ln K, and we have come across this equation, right. So, minus RT ln K is equal to just interchanging the ln to the log scale. Therefore, it is equal to minus 2.3 RT log K, where R is the gas constant, okay. The values are provided and T is at the absolute temperature scale. Okay. Now, at 25 degrees Celsius, we are going to, you can just change it, and you are going to if the T term you are removing and the R term you are removing, okay, and in kilojoule you are measuring, this is the, you just remember this value, that the delta G0 R is equal to minus 5.708 log K, okay, for G that is given in kilojoules, okay, for G that is given in kilojoules. So, the generalized reaction, so after you find out the K value, okay, after you find out the K value, you may have to find out something else, okay. So, K, how you write K in terms of activity again? So, products divided by reactants, okay, the ratio, okay, of the products divided by the reactants. So, here activity of D to the power D, activity of E to the power E divided by activity of B to the power B and activity of C to the power C. Okay. So, this calculation will tell us in which direction it is moving. Now, so that was the standard state. Now, you are going to move towards any other condition which is not at standard state, that is not at 25 degrees Celsius and not at 1 atmospheric pressure. Okay. See, most of the time if you are if you are doing any chemical oceanography, then your pressure is not 1 atmospheric pressure. Okay. Your pressure can vary with depth inside the ocean, and in other aquatic systems also, say suppose if you are looking into groundwater, then your pressure may change. Okay. It will not necessarily be 25 degrees Celsius also. So, in any other condition, what is the free energy of reaction? Okay. For that, and that this encompasses the majority of our problems. Okay. The standard temperature pressure conditions are very theoretical, that which can be done in the laboratory. Okay. We are going to experimentally find out, determine certain values. So, that we are going to keep the temperature constant at 25 and pressure constant at 1 atmosphere. Now, how do we do it in normal conditions? Normal means the aquatic conditions. Okay. Is a specific reaction at equilibrium? Okay. What kind of spontaneous reactions is going to happen, in which directions? These are our questions in those conditions. Okay. Now, the way we do it is to calculate the reaction quotient using the observed concentrations, and we are going to convert it into activities. We are not going to use concentrations here, we are going to convert it into activities, and we call this, again as I have already said, this is called Q, to distinguish it from K, which is at equilibrium. So, if the product divided by the reactant is at equilibrium, then we call it K. If it is in any other condition, we will call it Q. Okay. So, comparison of the Q value from the K value will tell us how far it is from the equilibrium and which direction it is supposed to proceed. Okay. So, the free energy change, okay, can be written as delta Gr, this one free energy of reaction, is equal to delta G0 R, that is at a standard temperature pressure, plus 2.3 RT log Q value. And what is Q? Q is AD to the power D, AE to the power E divided by AB to the power B and AC to the power C. And what do you mean by in situ? In situ is in the in situ conditions. Okay. What is the activity? What is the temperature pressure? Okay. So, this is just we are going to write, define how is Q. So, basically this is our equation. Okay. Basically this is our equation, and Q is sometimes also called the ion activity product, IAP. Okay. It is also called the IAP value. Now, if we are going to use the K term, if you are going to replace this with K term, how it will be? Delta Gr is equal to minus 2.3 RT log K, okay, this one, plus 2.3 RT log Q. Okay. From here we have this term, and only delta G0 R value, this we are going to substitute this term minus 2.3 RT log K. Okay. So, delta G0 R which is equal to minus 2.3 RT log Q, we are going to replace here in this term and we are going to find out, okay, this term is replaced. So, delta GR, now we are just going to rearrange the terms and 2.3 RT log Q by K. Why Q by K? So, this is negative term. So, in terms of log, this comes in the denominator, and if Q by K, we are denoting it using this omega sign, then it is 2.3 RT log of omega, where omega is equal to Q by K. If K is equal to Q, that means my omega is equal to 1, then the delta GR is equal to 0. This reaction is at equilibrium and this free energy state is at its minimum state. So, that is because it is equilibrium state, right. Every time we are trying to move towards equilibrium state. So, my delta GR equal to 0 at equilibrium. If my Q is greater than the K, that means my omega is greater than 1, right, because my Q is greater than K. Then my delta GR is greater than 0. Okay, this is greater than 0, then the reaction goes to the left, that means it has too many products as compared to the reactions. So, it is a reversing reaction, then the reaction will move in the opposite direction. If my Q is less than K value, then my omega is less than 1, then my delta GR is less than 0, therefore, the reaction goes towards the right and my reaction is going to proceed in that right direction. Okay, do you understand this? So, whether a reaction is going to move in the forward direction, whether it is going to move in the backward direction, depends how you find out this. So, you need to calculate the delta GR. From the delta GR value, you are going to say whether it is a forward reaction, whether it is a backward reaction, whether the reaction is at equilibrium. Okay. So, with this I will stop today's lecture and we are going to discuss more in the next lecture. Thank you.